Section 1.1. We're going to start with equations today, okay? So we have done nothing with equations so far. You've done everything with expressions. Expressions means that they don't have any equal sign, or maybe a better way of saying it is the equations means they do. All right, so we're going to be dealing with solving equations. Let me get my paper. All right, so as we look at that, the first thing we probably want to talk about is what we mean by a solution. A solution of an equation is a value of x, or whatever variable we're using, that produces a true statement. So what do you think I mean by a true statement?
It makes what's on the other side of the equal sign actually a reality.
Yeah, and I'm going to change just slightly what you said. That was a good description. I want actually, instead of saying the other side, I want both sides to have the same value, right? So sometimes the variable will be even on both sides, and so we actually put it into both sides. So it makes both sides of the equal sign have the same value. That's what a solution actually is. So the first thing we're going to look at is actually deciding whether or not something is a solution. Because all the way along, this is one of those things where you should know whether or not your answer is right. And you can know whether it's right, not even by checking the back of the book or by clicking on that button that says, like, did I get it right? And it checks marks it right in my math lab and says, yay, or it says, no. You don't need that, right? You could actually check your own solution. Agreed? How would we do that?
By plugging it in.
Yes, by plugging it in. So we can take the variable, however many variables there are in our equation, and we can plug in or replace or substitute the value for the variable. So on this one, we have, the question is whether the value -2 is a solution. So we're going to replace or plug in or substitute the -2 for the x into our equation. And our question, really, sort of this is a question mark for an equals, is whether or not it actually equals what's on the other side. That's our question. Okay, we want to know, do the two sides actually equal? So I have an intermediate algebra class, and I've had several students asking me this week because they took a test as well. Theirs is all online. They keep asking me if the negative on the bottom means anything different than the negative in front or the negative on the top. And do you guys remember the answer to that question? No, it doesn't. So the negative, no matter where it's located, numerator, denominator, or out in front, all mean the same thing. So this is equivalent to saying I have -1/2 minus 1/2 on the left. What is -1/2 minus 1/2? It is actually -1. And that's exactly what the right-hand side actually said, right? So it checks out. They are equal on both sides. Let's make sure we answer the question. The question said, is this number a solution?
Yes.
And the answer is yes. So our answer on this one is actually not a numerical value. It's a word. It's a yes or a no. Okay? So we should be able to check any solution or potential solution that we get and see if it works by plugging it back in. And if you want to plug it back in, more quickly than doing it by hand at that point, grab a calculator, substitute something like that, that's totally fine. But just be aware that you can always do that. Okay, so knowing how we can check our solution is a good feature of equations. But also knowing how to find a potential solution is a good thing to know. And I know that most of this should be sort of review. You start learning how to find solutions, learning how, in Algebra 1, which was probably 8th or 9th grade. And so the process by doing that is a long process because there's lots of things it involves, but that's where it first starts, is in Algebra 1. So I have a couple of examples right here. The first one's a lot simpler than the second one just because the second one, number 3 here, has fractions. But this one right here, there's more than one way to do the problem. So somebody give me a suggestion for what we might try to do first on number 2.
Factor.
I don't think factoring is going to help, because we want to factor usually when we have quadratics, and these are still linear equations. Another thought. Distribute might be a good thing, and then maybe that's what you meant, Anna, is to sort of unfactor. So we will unfactor or distribute the -3. I think that's a good first step. Again, not the only first step, but it's a good solution, or a good place to start. So if I distribute this, I have -3x plus what? 15. Now, a few of you, when you were distributing negatives, struggled. I have graded that problem on the test. So be very careful that you distribute the negative to everything. So this negative here affects the -5 to make it positive, right? It's a silly thing to sort of make a mistake on, but it's an easy thing to make a mistake on too, just to overlook it. All right, now I've got that on the left. I've got the 4 minus 2x still on the right. What's next?
You'd subtract and not 2x, add 2x to.
Okay, so let me say it a different way since I've got a couple different things being said. What's the goal at this point?
Get x.
To get x by itself. The goal is to get x by itself. So in order to do that, the first thing I might want to do is to do what? What's that? Okay, so we need to collect items, right? So to collect all of the things that have x to one side and all the things that don't to the other. So it's probably going to involve some addition and subtraction. Does that make sense? Okay, let's deal with the x's first. What might we want to move in terms of the x's to collect them all on the same side?
-3x.
You want to move the negative 2x. So how do you want to move it, Andre?
You could either add it to the other side.
Okay, and I'm going to change again the language used just a little bit. We're going to actually add it to both sides, right? And in doing so, it will eliminate it from one side. If I didn't want to add the 2x, what else could I do?
Add the 3x.
I could actually add the 3x to the other side. And are both equally good solutions? Sure, either one is an equally good step. So I'm going to deal with the x's first, and then we'll deal with the constant second. If you're adept at doing this and you want to deal with both at the same time, fantastic, go for it. It's cool, okay? So right now, what does this leave me with in terms of x's on the left?
1x.
Close. Negative 1x. So we can either write negative 1x or just write negative x. I still have a 15 on the left. And I have what's on the right? Just the 4. Okay, so since I decided, Andre decided actually, but I was cool with it. Since I decided to move the x's to the left, what does that mean I need to do with the constants? They got to go to the right, all right, the opposite side. So instead of moving the 4 like we could have done, that was Anna's suggestion and totally a good suggestion too, I want to move the 15, okay? Just because I moved the x's to the left, we'll move the 15 to the right. So how will I move the 15? Subtract the 15. I'm running out of space. Let me make my stuff smaller. Okay, so if I subtract the 15, I still have a negative x on the left. Anything else on the left? Nope.
No.
Negative 15 and positive 15 add to 0, yeah? What's on the right? Negative 11, very good. Okay, I've got negative x on the left, I've got negative 11 on the right. What's last?
Divide negative by -1.
Yeah, either divide or multiply by negative 1, yeah? So if I take negative 11 divided by negative 1, what will x equal? 11. How could I make sure I'm right? Yep. So we could plug the 11 back into the equation. And in this case, since there's an x on both the left hand and the right hand side, we'd have to put it into both locations for x, right? And simplify both. Just for fun, in this example only, I'm not going to do it on every example, but let's just try it, make sure it works. So if I put in the negative, I have a negative 3. I have 11 minus 5 in parentheses, right? And on the right I have 4 minus 2 times 11. This is where that order of operations stuff that we worked in the last chapter is really important. You need to make sure we get our order of operations right. So inside the parentheses first, 11 minus 5 would be 6, and then negative 3 times 6 would be negative 18. And we got to make sure we do that in the right order. On the right-hand side, there's no insides of parentheses to simplify. So do I subtract first or do I multiply first? Multiply first. 2 times 11 would be 22. So then I have 4 minus 22, which would be negative 18. Does it check out? It does. We've got the right solution. Okay?
Is it alright if I go fill this up with water?
Yeah, go for it.
Okay, I'm dying of thirst from these crackers.
Okay, second example, I mentioned before we even started it, it's kind of messier just because of the fractions. But again, things that we did in Chapter P, the things we did before, are going to prove helpful if we remember them through the process. There's more than one way to do this problem, but the way that seems most reasonable from what we did back in Chapter P is simply to get rid of the fractions. And let's be honest, raise your hand if you really enjoy working with fractions anyway. Oh, we've got one, but just one. Right? 1 out of like 20-something who are here today. So most of us don't really want to work with the fractions. We'd kind of like to get rid of them if we can anyway, yeah? Fewer mistakes made. So if we take a look at the denominators, I've got a 2, a 5, a 6, and a 3. And I need to multiply by what's called either the least common denominator. or sometimes we call it a least common multiple, the multiples of the denominators, so that it will eliminate all of the denominators at once. So clearly I gotta multiply by something that's got a 2 in it and something that's got a 5 in it. But once I get to 6, 6 is actually the same as, like, what do you get when you factor 6? 2 times 3, and I've already got one of the 2's, so then I need the 3. So I need to multiply by something that's got a 2 in it, a 5 in it, and a 3 in it. And if you take a look at the 2 times 5 times 3, this 2 will eliminate with a 2 times 5 times 3. The 5 will eliminate with 2 times 5 times 3. 6, well, that's 2 times 3. That's in my list, right? And 3 is in my list. So if I multiply by 2 times 5 times 3 on both sides of the equation, because we are dealing with equations now, I will be able to eliminate all of my denominators. So we're multiplying by 2 times 5 times 3 on both sides. Now, as we do that, we have to remember that we will be distributing that to each fraction that we have, right? So if I multiply 2 times 5 times 3 times x over 2, what will happen to the 2 in the denominator? It will cancel. And that's kind of the goal, really, right? So the 2's will cancel, and I'll be left with the 5 and the 3, which is 15. So I'll be left with 15 times the x that's there, so it's 15x. I'm going to go ahead and put the addition sign. We're going to do the same thing with the second fraction, x over 5. The 5 in the denominator will cancel with the 5 that I'm multiplying by, correct? So there's no more 5 in there, but there's still a 2 and a 3, and 2 times 3 is 6. So I still have a 6 that I'm multiplying the second fraction by, the x. All right, moving to the right-hand side of the equal sign, I have x over 6. This 6 will reduce with what over here?
3.
The 3 and the 2, right? Like that's why we chose these numbers, is so that I'm removing all the fractions as I go. It will reduce with the 2 and the 3, leaving me with a 5. This 5 will then be multiplied by what remains, which is the x. So I have a 5x in that fraction left. 1/3. What will the 3 as a denominator cancel with?
3.
The 3, leaving me with the, the 2 and the 5, which is 10 times this -1. So I have -10, like Rebecca said. And there are no more fractions.
Is there any other way to do that?
Yeah, you can get a common denominator, but essentially you'll have to multiply by the number eventually anyway. At some point, you're going to do some kind of cross multiplication where you eliminate the fractions.
I'm just asking because I've never done it that way.
Yeah.
And it kind of lost me in the middle of it, but I mean, I get the idea of it, but.
One of the things that you could do, Jeremy, too, let me move this down and show you, is you could write this out as 2 times 5 times 3 times x over 2 plus 2 times 5 times 3 times x over 5. 2, oops, that's not a plus, there's an equals between there. 2 times 5 times 3 times the x over 6. You're actually showing the distribution. Are you with me so far?
Mm-hmm.
And then you've got the 2 times 5 times 3 times your 1/3, -1/3. Or you could put the negative at the beginning of that, either way. If you do that like this, get a different color, then you can see the reducing step like this, which might help. You can reduce it like this. This 2 and the 3 reduces with the 6 here, and then the 3 reduces with the 3 here.
Okay.
That's what we're really doing.
I got it now.
Got it? Does that help?
Well,
Yeah, it does.
where do you get the two factories from?
I looked at all the denominators.
So you just,
Every piece that the denominator is, because the denominators that I have are 2, 3, 5, and 6,
so why didn't you take the six?
because 6 is already 2 times 3, and they're already in my
Oh.
list. Yeah, so all I did was factor all the denominators, and I used all the pieces, the prime pieces that are in the denominators as my list of numbers to multiply by. Okay, 15x plus 6x, that simplifies, yeah? What does that become?
21x.
21x. So I have 21x on the left. I have 5x minus 10 on the right. Now what?
You move the 5 over.
Sounds good. Let's move the 5 over. How will we do that, Rebecca?
You subtract negative 5x to both sides.
Okay, so we're going to subtract 5x is what I think you meant, right?
Yep.
To both sides.
Sorry.
Yep, it's okay. So I have 21x minus 5x. What will that give me? 16x. The 5x minus 5x, that's 0, right? But I still have a negative 10. And then what? Divide by 16. Now, technically speaking, we have an answer, but it's not reduced. How would I simplify 10 over 16?
Take out 2,
Yeah, they both divide by 2. So if I divide 10 by 2, I get
negative 5.
-5. And if I divide 16 by 2, I get 8. And 5 and 8 don't have anything in common except for 1. So at that point, it's simplified. This one's actually nice enough that if you wanted to, you could turn it into a decimal because it stops. It's called a terminating decimal. And if you did, it would be an acceptable answer as well. What is 5 over 8 as a decimal? Just for fun, let's figure it out. Somebody have a calculator.
Is it 0.62?
That sounds right. And it'll be negative, right?
625.
I think it's 625. Can somebody confirm that for us? It is. Thank you very much. So we have negative 0.625. So either of those would be perfectly reasonable solutions. If you didn't have a calculator, or if your calculator gave you a decimal that didn't stop, like it was repeating like 0.33333, my math lab's probably not going to be okay with that as your solution because you would have had to round at some point when you're putting it in, okay? So either of these answers is fine because neither one of them had to be rounded. Does that make sense? All right. I know this one was a more complicated one, so when you see examples of this in your homework or whatever, make sure you're paying very careful attention. My math lab might show you an alternate way, of course, to do the problem as well, which is totally fine. Eventually, you're going to do the same stuff. You're eventually going to have to cross multiply and get rid of the fractions to solve that. It's going to be 5 over 8, negative 5 over 8. All right, we're going to talk about how we classify equations. There are 3 classifications or ways of describing equations. The first one is called an identity. An identity is an equation that is true for all real numbers in the domain. In other words, x can be anything and it will work. For example, I'll give you a real quick example right here. Let's say, for instance, that I had 1/2 x equals 0.5x. That's an identity. No matter what x is, it is true. Okay? A conditional equation, these are the kind we normally have, means that it's satisfied by one or more real number, but not all real numbers. That's exactly what the last 2 were. We got one solution in each case. It wasn't all numbers that were solutions, and that's where most of our equations fall. Most of them are conditional equations. And an inconsistent equation, what do you think that one might be? No solutions. It's neither one. Yeah, it's neither one, so it's no solution. So I can give you an example of that as well. Let's say, for instance, that at some point here we had x plus 7 equals x plus 2. There is no number for x that I can plug in that will make that true. These are flat out not equal, ever. That would be an inconsistent equation. Still an equation, not a very exciting one since it's got no solution, but it is an equation. Expression on each side, equal sign in the middle. Okay, so we've either got infinitely many solutions, or all solutions. We have a few, or maybe just one solution. And in particular, when we're working with equations that are linear, which is what this section is, it is one solution. And then the third option is no solutions. So we're going to look at some equations and decide which type of equation it is. Does it have one solution, all solutions or no solutions. And in order to do that means we have to solve it and figure out what's the solution. Make sense? So if at some point we get to a place where we have it like number 1, where we can see very clearly that no matter what we put in it works, or like number 3, we can see very clearly that no matter what we put in it will never work, then we can stop. Okay, so at whatever point we see that happen is the point when we're done with the number 1 or a number 3 type equation. So let's do an example. All right, what would I do to solve, okay, so like I just did in the last two, our goal is to solve what we have. What do we do to solve number 4? Don't overthink it. What am I doing on the left?
We add.
We're going to add 2a and 3a, and we're going to get 5a. Yeah. You guys know this. Don't look at me like I'm crazy. 5a equals 6a. Now what?
Don't you add subtract 6a from 5?
You can. We can subtract the 6a to the left. What will that give us on the left?
-1.
Not quite. It'll give us 0 on the right. What will it give us on the left?
-a.
Negative a. So I've got negative a equals 0. So what's a?
Consistent.
0.
A is 0, right? We divide by -1 or multiply by -1. A is 0. Okay? Now, you can check and make sure that it works, right? 2 times 0 plus 3 times 0 equals 6 times 0. Does that work? Yeah, it's not real exciting, but it works. So what kind of an equation is this? It's conditional. We had 3 types. This one is a conditional equation. And that's what we're actually asked to do here is to classify. Okay, so we need to make sure we identify which one it is. It's conditional. Let's try number 4. What would I do on number 4 to figure this one out? I'm sorry, 5. Looking at the 4 at the beginning of it, but then number 5.
What is this thing would be to distribute?
The easiest thing I think would be to distribute first. So if I distribute on the left-hand side like Jonathan said, what will I have? 4y minus 4 on the left, and I'll have 4y minus 4 on the right.
That's an identity right there.
That is an identity right there. They're exactly the same on both sides, right? Now, if you didn't notice it right away and you keep solving, it's okay. But at some point along the way, you should find out that these are exactly the same. That is, the two sides of the equation are, and if that happens,
Work it out fully then?
what's that?
For identities, do you not expect us to work it out fully?
Well, the directions, remember, Anna said to classify, right? They just say classify, so we're just trying to get to a point where we can say that this is a conditional, it's an identity, or it's inconsistent. So at the point when we recognize that both sides are the same, we have an identity and we're good to stop. Okay? If you do keep going, it's not going to hurt anything. How about, I mean, you know what you think is going to happen on 6, right? You think it's going to be inconsistent because we haven't had one of those. So that's the expectation. Of course, that doesn't always work when you're doing your homework set. But let's check it out. What happens when I start working on this one?
You combine the x terms on the left side.
I do, and I get 5x, right? So I have 5x on the left, I have 5x plus 1 on the right. At this point, you should be able to look at this and say, that's not possible. But let's say, for instance, that you're just caught up in the moment of keeping working through the problem, okay? And so you keep trying to solve. If you were to keep trying to solve this, what would be your next step?
Subtract 5x.
You would subtract 5x. I would just want to show you what will happen if you keep going eventually, and they always happen with these. What happens on the left? You get 0. What happens on the right? You get 1, and at this point, you better recognize there's a problem, right? 0 equals 1, and you say, no, it doesn't. No, it doesn't, right? At some point, you get something that does not work, and that makes this an inconsistent equation. It's not possible. There's no solution. When we're talking about classifying, they are identifying one of these 3 equation types. So the answer still could be no solution, but because the answer is no solution to what is the solution kind of a thing, that makes it classified as inconsistent. Yep. All right. We're going to switch gears just a little bit. You guys worked with some absolute value stuff in chapter P. We're going to work with absolute value equations now in chapter 1. Some reminders about absolute value equations if you haven't dealt with them in a while. The first thing you need to do is to isolate the absolute value. And the second thing, and this is in big bold type because it's the one that's easiest to forget, is you have to check your solutions. And there's a very good reason for this. As we work through absolute value equations, sometimes you will find quote unquote solutions that don't actually work in the original equation. Okay? Because of the way you go through solving them. It happens on quadratics as well. We'll see this happen again later on. It'll happen sometimes on square root equations. The process by which you solve sometimes creates things that appear to be solutions in the end, but don't actually work with the equation as it was given at the beginning. So we need to be very, very careful with absolute values. Okay? So the first issue, however, is that we have to isolate the absolute value. So right now on number 7, there's an absolute value on the left, but there's some other stuff too. So our goal is to get absolute value equation all by itself, or the absolute value part all by itself, and then everything else onto the other side. So what would be the first thing we would need to do on number 7? Subtract the 6, I agree. And I'll actually show you too in this one, it's going to have a problem. I'll show you why it has a problem. So we're going to subtract the 6. So if I do this, I'm going to get absolute value x plus 9 on the left. And what am I going to have on the right? Negative 6. Okay, if you get carried away and you keep going on this problem, you are going to get solutions that don't work. And the problem is right here. What does this say? Well, it says that there's an absolute value, and it equals negative 6. And Holly's shaking her head, and a few others of you are as well. Why? Why are we shaking our head? That's right, absolute values can't ever be negative. Agreed? Yeah, I mean, they can't. An absolute value is a positive quantity. So if I continue in this problem, I am going to get potential solutions, and they are going to fail. All right? So this would actually give me no solution on this. Now, we weren't asked on this one to classify. If we were, what kind of an equation is this? It's inconsistent because there is no solution to this equation. At the point here where I recognize there's no solution, there's no sense in continuing the process to try and solve it because it won't be possible. All right? So if at some point you get absolute value equals a negative, you can stop. There's no way that's going to work, and you have no solution. Let me show you what happens on number 8 when that doesn't occur. That is when we don't have something, causing problems early on. Okay, so again, our goal is to isolate the absolute value, right? I want the absolute value part by itself. So we are going to work order of operations from the outside inward when we solve equations. Right? Order of operations when we're simplifying things is to start from the inside and work our way out. But when we're trying to get this, a piece of it alone, we work from the outside in, moving stuff, getting rid of it to the other side. So looking at this one, what's the first thing I would need to do to get the absolute value alone? Subtract the 6. Very good. Okay. I need to get the 6 on the other side of the equation. So if I subtract the 6 at the beginning, it won't be here. And now I'll just have the negative 4. Don't forget that negative. And the x plus 3 in absolute values. What's negative 2 minus 6? Good job, negative 8. Okay, still working from the outside in. What would be next? Good, we would divide, all right? Because right now this negative 4 being right next to the absolute values means it's multiplied. The opposite of that is division. So we are going to divide by negative 4. So on the left-hand side, the negative 4's cancel, that was the goal. And I'm left with the absolute value of x plus 3. What do I have on the right? I have a 2. Good. Okay. Now, it always feels funny to write, at least when I know I get funny faces from people when I write what I'm about to write. So let me explain first. I'll write second, then I'll explain again. Okay? In order to get an absolute value of 2, what's inside of the absolute values would be or could be a 2, right? What else could it be? It could be a negative 2. Like the actual quantity of the stuff inside here that I'm covering up could be negative 2. I take the absolute value and I get a 2. So the next step is to take what's inside of the absolute value, which ours is x plus 3, and set it equal to 2, and set it equal to negative 2. Now, what I'm not doing is I'm not saying the absolute value is a negative value. I'm not saying that. What I am saying is that the stuff inside of here could be negative. Okay? So again, I'm not setting something equal to negative 2 as an absolute value. That's what it kind of looks like. It's not what's happening. I take anything that's on the inside of the absolute value, I set it equal to the positive 2 that's already there, and I set it equal to the negative 2 that it could have been. Those are the 2 options. And then we solve both of those equations. So if I have x plus 3 equals 2, and I solve that one, what do? Subtract a 3. X is on the left. What's on the right? Negative 1. So this is one potential solution. How about the other one? X plus 3 equals negative 2 on the second equation.
Negative.
Subtract a 3 still. So x is equal to negative 5. There are 2 potential solutions to this equation. And we can check them by doing what?
Bring them back into the equation
Plugging them back in. Where would we plug them back in?
for x.
For x, but where? Like, at which step along the way? I didn't ask that very well.
The last one.
Nope. The original is right. We've got to go back to the very beginning because we did a lot of steps throughout, right? And potentially we could have made mistakes throughout those steps, right? The only way to know if this really satisfies the original equation is to use the original equation to plug it back in. So I told you we weren't going to check every solution on these, but this is one where it says, right? Always check your solutions. So we're going to do that. So we're going to go back to the original equation, which said 6 minus 4. Absolute value of x, so negative 1, that's one option, negative 1 plus 3. And I want to know if that equals negative 2. And then the other one is 6 minus 4, absolute value. I have negative 5 plus 3 equals negative 2. This is a lot like the very first problem on your test. And a lot of you still wanted to subtract 6 minus 4 as your first step. It's not the correct order of operations, right? Subtraction never is the first thing, unless it's occurring inside the absolute values, which we do have that here. So let's look at the first one I have, this one right here. Inside the absolute values, I have negative 1 plus 3. That gives me 2. Okay, so I have 6 minus 4 times the absolute value of 2. What's the absolute value of 2? 2. So this is actually just the same as 6 minus 4 times 2. I'm running into my other piece. Let me move it. Okay. 4 times 2 would be 8, because order of operations says I should multiply before I subtract. And then 6 minus 8 is negative 2. And how does that compare to what we wanted it to be? It works, right? So this, it really is, this potential solution really is a solution. It worked. Now, let's do the second one. I moved it to the bottom. You know what, let me do this. Give myself a little bit more space. All right, absolute values. We start inside of the absolute values again, right? I have negative 5 plus 3, which is negative 2. So I rewrite all the pieces before that. 6 minus 4, absolute value negative 2. What is the absolute value of negative 2? 2. Now I have 6 minus 4 times 2. Order of operations, multiply first. 4 times 2 would be 8. And it's negative because there's still a subtraction sign between. And then 6 minus 8 is negative 2, which is exactly what we wanted it to be. So this second potential solution, again, is an actual solution. Now, there's a name, I don't know if your book gives it this name early on in this, but we'll see it later on if not. If you find a solution that doesn't work and you have to be like crossing it out and you're like, yeah, that doesn't work, there's a name for that. It's actually called an extraneous solution. Maybe you've heard that before. It means it was a solution as you worked it out, but somewhere along the way in your work, you actually did something that caused it to not be a solution. It's not a real solution. It's called extraneous. All right, I have a couple more problems for us to take a look at today. They're both I think so. Yeah, they're both rational expressions that are turned into equations. And they're much like the very first one we did. I think it was problem number 3 or something like that, where we looked for the common denominator and got rid of the fractions. But they're messier because they have variables in the denominator as well. So as we're looking for this, like we mentioned on the one before, our goal is to get common denominators. We either get common denominators on each side and then we cross multiply, or we eliminate fractions from the beginning, which is usually the way that I go about it because I want to get rid of the fractions. And again, we need to always check our solutions, and there's a really good reason for the checking the solutions on this one. And it isn't so much like we need to make sure it works, although that's not necessarily a bad thing. What we really need to make sure is that what doesn't happen to these fractions? What would be a problem?
If the denominator equals 0.
You got it. If we find a solution that actually ends up making the denominator equal to 0, that's a problem, right? It wouldn't really be a solution. So our goal when we check the solution is you certainly can check and make sure it really works. But the places where it's going to really cause problems is if it has a denominator equal to 0. That's actually what we don't want to have happen, okay? So our primary goal in checking solutions is to make sure denominators don't equal 0. Okay, so taking a look at this one, the first denominator is x minus 1. The second denominator is x plus 1. And then the third denominator is x squared minus 1. Now, x squared minus 1 looks like a polynomial form that we saw happen back in section P5. And we did something with it when we factored it that was special. What kind of a factoring formula did we see here? Difference of squares. Very good. So if I were to take, I'm just going to rewrite the right-hand side for the moment. 3 is going to stay on the top. And I'm going to rewrite the denominator so that it's factored. How will that denominator factor?
X minus 1, x plus 1.
And what do you notice about that? It's the same denominators that we see happening on the other side of the equation, right? And that will typically happen on these problems. You will typically see repeated denominators happening throughout the problem. It's not an unusual situation at all. So if I'm looking at these 3 denominators, there's really only 2 pieces that are showing up repeatedly. Agreed? Okay, it's x minus 1 and x plus 1. So this is much like the earlier problem that I did. I'll write it out more carefully this time just because I think I lost some of you when I was writing it out sort of abbreviated. We're going to multiply both sides by those 2 pieces of the denominator, x minus 1 and x plus 1. So if you don't need to see this step where I'm writing so much out, you don't have to write it all out this way. But for those of you who do need to see it, I want to go ahead and show it. So I'm going to multiply x minus 1, x plus 1. Whoops, that's okay. By 4 over x minus 1. And I'm going to multiply x minus 1, x plus 1 by 9 over x, what was it, plus 1. And I'm going to multiply x, well, I'll just rewrite it the way it already was, 3 over x minus 1, x plus 1 times the x minus 1, x plus 1. And I'm doing this, I've got an extra parenthesis back there. Let me eliminate that. Here we go. I'm doing this, and I'm allowed to do this, because if I multiply every piece of an equation by the same number, right, I've balanced the equation. As long as I do something across the board to everything, I'm allowed to do that. So we notice on our first set right here, where we're multiplying by the 4 over x minus 1. I still have an extra parenthesis there. Let me get that one rid of that one too. There we go. What do you notice happens to the x minus 1s here?
They cancel.
They would cancel.
So that'll leave us with just x plus 1.
And the 4, right? It'll still leave us with the 4. So I've got an x plus 1 still here and a 4. And those are the only pieces that will remain from this set. Moving to the second set, what do you see happen? The x plus 1s cancel. Right. So here's x plus 1s that cancel. So on that set, I'm left with, well, there's a negative still out here at the beginning. There's an x minus 1. And what else is there here? In this set? There's a 9. Oops. A 9. On the other side of the equals, what's going to happen? Everything's going to cancel on the denominator, right? And what am I going to be left with? A 3. That is a way simpler equation than where it began. Don't you agree? Way better. What would I do next? Multiply, distribute, exactly. So I would take the 4 and distribute through here. What would that give me? 4x plus 4. And then I have to be a little bit careful here in the middle because there's a negative and a 9, both that need to be distributed, right? So let me distribute the 9, and then we'll go ahead and worry about the sign. So if I distribute the 9, I've got 9x, and I've got 9, and then the negative should change both those signs. So the 9x will be what? Negative, and the 9 will be positive. Be careful about signs. Simple sign mistakes just throw things all to the wind. And I have a 3 on the right. Okay, I can simplify still on the left-hand side. What do I have? 4x and negative 9x, which would be negative 5x. What else? 4 and 9, which would be 13. Equals 3. Now what? Subtract the 13. I have negative 5x on the left. What's on the right? Negative 10. Now what? Divide by negative 5. X will end up equaling, like you guys said, 2. Now, at the very, very minimum, you need to make sure that doesn't make any denominator equal to 0. Does it? No, it doesn't. Sort of on the upper end of what you can check, you could actually check and make sure that it works in every piece to make both sides equal. And I know you guys can check that too. But the biggest problem will be if it makes the denominator equal to 0, and this one's okay. All right, we're going to try one more. You ready? It's a very similar problem. Tell me what we're going to do first.
Factor out the bottom of the
On the right-hand side, right, Anna? Yes, you got it. So we're going to factor the denominator over here. How will the x squared minus 4 factor?
X plus 2, x minus 2.
X plus 2 and x minus 2. And we notice then that those are the pieces that are on the other side, right? So we can use that quantity, x plus 2 and x minus 2, to multiply both sides of our equation.
Could you just go from that right there and like not go through each of the steps, just cancel it out from that?
You can. You do need to be careful when you do it, that you're sort of distributing as you go mentally, right? Like, for instance, Jeremy, I wouldn't want you to accidentally mark this out as x minus 2 and mark this out as x plus 2 and somehow end up with a 3 and a 4 only. Because you have to do each fraction. So you have to be careful. Like on the first one, as I cancel, I can only cancel the x minus 2, which means the 3 that's in the numerator is still left multiplied by x plus 2. And if you're okay to jump to that step, then that's totally cool. That's actually what I was doing when I originally did the problem, like in number 3 at the beginning of this problem set. Okay? If I do this, as long as I'm being careful, I can avoid writing out the next piece, the one that I just wrote from the last problem. X plus 2, x minus 2 with the 4 over x plus 2 would cancel the x plus 2's. I'm left with the 4 and the x minus 2, right? On the right-hand side, of course, it all cancels out, so that, doesn't have any problem over here. And I'm left with 7x minus 2 on the right. Okay, clean up the left-hand side. I'm just going to let you do it. Just clean it up and tell me what you get, and we'll make sure, clean it up, combine all the like terms, simplify to the point. Don't move it to the other side. Just simplify the left-hand side for me. 7x, and then what? Minus 2. Does everybody have 7x minus 2 on the left? And what do you notice is on the right? The same thing. What type of equation does that make this? It makes it an identity. Now, if I'm classifying it, I will classify it as an identity. If I'm just asked to find the solutions, what's the solution to this equation?
Except 2 and -2.
Very good, Alexis. I'm so glad. Yes. Okay, so what's wrong with those numbers, Alexis?
They make the denominators.
Yes, so this is all real numbers except 2 and -2, because those would make the denominator 0. And if you will go back to your definition of what a identity is, read me what it said about identity. Jonathan's got it. What do you have, Jonathan?
True for all real numbers in domain.
Ah, it said true for all the real numbers in the domain. What can you tell me about 2 and -2 here?
They would make the domain true.
Right, they are not in the domain. That's another way to say that. They're not in the domain. So it still makes this an identity. The fact that I eliminated 2 possible answers doesn't make it not okay. They're not in the or in the domain at all to begin with. Jeremy.
Unlike my math lab or anything, so would you put an answer would be all real numbers that don't equal 2 or -2?
Probably. Yeah, it would probably say something like all real numbers like I have here. And then it'll say something like x does not equal 2, -2.
Okay.
That's probably how it would have you write the other piece of it. Good question. Any other questions on that one? That one's a little bit weird, right? Yeah, because we still can't use really all the numbers because of the domain issues on this one.